Testing, can you hear me? Hello, can you hear me? Testing. Okay, the video should be live right now. So, I'm going to be learning Calculus 3. I took a long break from Calculus. Also, I just want to preface that I'm not like a math expert, I'm just learning Calculus. So, I would be reading, I would be even skipping through, but uh, I'm just a student. I don't want people asking advanced questions. Anyways, I'll just change to full screen right now. They say there's an update available. I just want to get rid of this thing. So last calculus stream I read about double integrals. I'm not good at them, but I did read them and get some understanding. I want to read about triple integrals. Maybe these two chapters I will do next stream. But this is really slow. Hold on. Alright. So I'm gonna go here to triple integrals. In double integrals over rectangular region, we discussed the double integral of a function f of xy of two variables over a rectangular region in the plane. And now they're using triple integral. You can define a rectangular box P in R3 as P is equal to xyz, where x is between a b, y is between c d, and z is between e f. Follow a similar procedure of what we did in double integrals over rectangular regions. We divide the interval a b into L subintervals of equal length. Same with y, same with z. Then the rectangular box is subdivided into LMN subboxes. With each box, so this giant box is divided into subboxes, and each box is delta x, delta y, and delta z volume. For each ijk, consider a sample point x. Okay, so this x star, y star, and z star is a random point inside the subbox. We see that its volume is delta x, delta y, delta z from the triple Riemann sum we get. So what is this exactly? This is the volume. What is this? We define the triple integral in terms of the limit of triple Riemann sum as we did for the double integral in terms of the if a double Riemann sum. So this is like applying f is defined with inputs x, y, and z, right? And we are doing applying the sum of f over this entire box. The triple integral of a function over a rectangular box P is defined as, so we some random x, y, z point in the box. We limit that to z. We limit L, M, and n to infinity. Fabini's theorem for triple integrals. If f of x, y, z is continuous on a rectangular box P, then this entire thing dv with respect to dv is equal to, so okay, we are varying x first, then we are integrating over y, and then we are integrating over z. And we can change the ordering as well. Evaluate the triple integral. Okay, let's try this. Also, I may be kind of sick. I have a I have a sore throat, so that's why my voice is kind of weird. Example 5.36. We have x plus y z squared. So let's just do 1. From -1 to +5, -1 to +5, we have this z squared. Let's just do x first, then we can separate them. And then this will be x squared over 2 from 5 to -1 plus y and z square would be constant in this case. We have x from -1 to 5, which is 5 square minus -1 square over 2, right? Y z square 5 minus -1. We have 25 minus -1 becomes 26, divided by 2 becomes 13. And then this is 6. I'll just write 6 over here. And now we can do it with y from 2 to 4. From 2 to 4 plus it with 6 z square is a constant. Y square over 2 from 2 to 4. You're left with 4 minus 2, 26, plus it with 6 z square, 4 square minus 2 square. 3z square. I'm doing 6 divided by 2. So 4 square is 16 minus 4. Is that right? Yeah. Now we do it with respect to z from 0 to 1. 26 is a constant. Z 0 to 1. 36 is a constant. Z square, z cubed, 0 to 1. We forget the 0, we are left at 26. This 3 over here is a constant, so we can divide it by 3. We are left with 12. And then we have z cubed, but this is just 1. Then we are left with 38. 36. This was 24, not 26. 12 plus 6. Um, 5 square is 25. Minus, oh yeah, minus, this becomes square. So it's 24 divided by 2, not 26 divided by 2. So this becomes 12. Whoops. Yeah, I get the point. I accidentally clicked the M. How do I get rid of this? 12, 24, 4, 4, 4, 4, 4, 36. Evaluate the triple integral where, okay, it's just the same thing. We now expand the definition of the triple integral to compute a triple integral over a more general bounded area E in R cube. General bounded regions we consider are of three types. First, let D be the bounded region that in is a projection of E onto the xy plane. Suppose the region E in R cubed has the form E is xyz xy for two functions z, u1 and u2. Where such that u1 is less than u2 for all x, y, and d as shown in the following figure. Triple integral over general region. The triple integral of a continuous function over a general three-dimension region is E, three-dimension region E, in R cube, where D is the projection of E onto the xy plane is, so we have this, and we have the integral with respect to Z first, and then we do the integral with the area. Note that the region D in any of the planes may be of type 1 or 2 as described in double integrals over general regions. If D in the xy plane is of type 1, then E is like this. Between AB, Y is between G1 and G2, C is between U1 and U2. Then the triple integral becomes like this. First between U1 and U2, then G1, G2, and then A and B. Violate the triple integral of the function f is 5x minus 3y over a solid tetrahedron bounded by the planes y is equal to 0, x is equal to 0, y is equal to 0, and z is equal to 0, and x plus y plus z is equal to 1. Let's think about this. So x plus y plus z is 1. It is clear what they're asking. So there's a tetrahedron like this, right? Like these are the three axes, and then there is a line. There's a plane crossing here, here, and here, and then this goes on top. Yeah, there's a plane crossing here. So bounded by the xy plane, and then I should open the 3D Desmos. Yeah. So this over here, bounded by the planes x is equal to 0. So x is equal to 0. So all of this is x is equal to 0. Okay, they mean bounded by the this yz plane, xy plane, and then the xz plane. So this tetrahedron inside over here. But it's not clear to me what they want to. They want to integrate this function, which is defined in this bounded box. But there is no z here, so what happens then? From 0 to 1 minus x minus y. Okay, let's try that. 5x minus 3 dz from 0 to 1 minus x minus, but there's no z though. So what do they mean by this? So we introduce a z. Yeah, that's what they seem to be doing. Now I have to, if I take one slice of this in the xy plane, z is the above one. XY plane, if I take one slice, it would be like this. This would be 5x minus 3y. If I take one slice of this, y would be equal to 1 minus x, right? So and then x has to be from 0 to 1. Yeah. And then I will replace y with this. But this will be this will be squared over 2. Let me think. So this will introduce a y where we will plug in 1 minus x. Same here. Here y square over 2. Plug in 1 minus y square over 2. Yeah. Y square over 2. Yeah. And then this will cancel out with the 3. Now we integrate this from 0 to 1. But we need to simplify this 5x square plus 5x cube minus it with 5 1. Yeah, minus x on minus x minus 2x plus x square. Two into a cancel plus x square minus 5 over 2 x cube. X minus 2. I'm not feeling really well. But anyways, I will just try to do this. I have 3x square plus it with 3 over 2x cube plus 1 1 minus 2x plus x cube. And then we have minus x plus 2x square minus x to the power of 4. I don't want to do all this. Finally, evaluate. Why didn't they take very long? They didn't expand this, violate this integral by obtaining this. In the end, it's 1 over 12. Finding the volume by evaluating a triple integral. Find the volume of a right pyramid that has the square base in the xy plane, a vertex at a point 0, 0, 1 as shown in the following figure. Don't we need double integral y triple? Okay, let's see what they're doing. In this pyramid, the value of z changes from 0 to 1 at each height z. The cross section of the pyramid for any value z is the square. Yeah, is this square minus 1z 1 minus c times it with a minus 1 plus c 1 minus c. So each corner at a particular z value. So at like one slice, the corners at each slice. Hence the volume of the pyramid pick is and I need to know what they're doing. If dx, dy, dz, they're multiplying in okay, there's no function over here. They're just multiplying tiny infinitesimal dx, dy, dz of each of these subsections, right? Okay, that looks agree. So, like in a 2D version, calculating the area, we're calculating the volume of this. So we have dz and then dy and then dx, right? And then we are calculating the volume of this, volume of this, volume of this, and so on for all the z's. So we're going through x is minus 1 plus c to 1 minus c. Can I draw over here? So x is from, so whatever z value we are in, so minus 1 z to positive c. So minus 1 plus 1 minus c to minus 1 plus c. And then we are going through the y values and c goes from 0 to 1. As we have already seen in double integrals over general bounded regions, changing the order of the integration is done quite often to simplify the computation. With a triple integral over a rectangular box, the order of integration does not change the level of difficulty of the calculation. However, with a triple integral over a general bounded region, choosing an appropriate order of integration can simplify the computation quite a bit. Sometimes making the change to polar coordinates can also be very helpful. So we consider this from 0 to y square, from 0 to x square, from 0 to 1. Verify that the value is the same if we let this equal to xyz. All right. We have 1 over 168, 1 over 168 over here, 2 times. And the ordering is different. They started with Z, then Y, then X. Over here, they started with X, then Z, then Y. In the end, they got the same answer, 1 over 168. Recall that we found the average volume of function of two variables by evaluating the double integral over a region on the plane, then divided by the area of the region. Similarly, we can find the average value of a function in three variables by evaluating the triple integral over a solid region and then dividing by the volume of the solid. Finding an average temperature, the temperature at a point of a solid E is bounded by the coordinates plane, that the plane xyz equals 1. Is T is equal to xy plus 8c plus 20 degrees. Find the average temperature over the solid. So we have this, but it's bounded by the coordinate plane and this plane. So this is exercise 5.42. xy, so we integrate xy plus 8z plus 20. Let's do dz first. It's bounded by this. So from 0 to 1 minus x minus y. 1 minus x minus y plus it with 4z square. Xy minus x square y minus xy square. You multiply all the ones and then we multiply the minus x. And then we multiply the minus y. And then we integrate all of this with respect to y. Then y goes from it's a tetrahedron, right? It's the same thing as before. Stuck on this. For a particular z value, y goes from at x is equal to 1, it's 0. So it goes from 0 to 1 minus x, right? 0 to 1 minus x. I think there's a better way to simplify all of this. Instead of y, I will write 1 minus x square, x square. I think it's not supposed to take this long, maybe. I should just keep the 4 outside. Minus x minus x minus 1 plus x squared plus x minus x squared minus 1 plus x plus it with x. Uh, Minus x squared. Set with my. Wait, no. To evaluate y first and then we plug in the. This is taking very long. I just want to know if I did the right method. Yes. Okay, they gave the answer straight away. Can I do the integral over here? Okay, I can. The triple integral of the temperature is 147 over 40. But the volume, we take 1 over the volume. Alright, and then we get 1 over 6. No, the volume itself is 1 over 6. And then we multiply these two, right? So we get 441 over 20 degrees. Yeah, I will just read the next chapter as well. Because most of my learning is done upstream. I just want to read the chapter in this screen. Review cylindrical coordinates. So as we have seen earlier in two-dimensional space, a point with rectangular coordinates xy can be identified with r and theta and the polar coordinates and vice versa. Where we have r cos theta, r sine theta, and then r square is equal to x square plus y square. So we have angle, we have cos, we have sine, and then we have, okay, so theta is defined, and then r theta, and we have z. A point with the rectangular coordinates can be identified with cylindrical coordinates and vice versa. Triple integrals can often be more readily evaluated by using cylindrical coordinates instead of rectangular coordinates. Some common equations of surfaces in rectangular coordinates alongside with their corresponding equation in cylindrical coordinates are listed in table 5.1. Cylindrical, circular cone, sphere, paraboloid. As before, we start with the simplest bounded region P in R cube, and we can state the following definition for a triple integral in cylindrical coordinates. So we have f of some r inside the box, some theta, some z. We are multiplying with that some r again, and then delta r, delta theta, delta z. If the function is continuous on P and the star r star theta star z star is any sample point in the cylindrical subbox, then we can define the triple integral as the limit of the triple Riemann sum provided the following limit exists. Violate the triple integral where the cylindrical box P is r from 0 to 2, 0 to theta, and then 0 to 4. So first we do 0 to 4, we calculate the z, and everything else would be constant. Then I think it would be easier to do sine theta, calculate the theta, and then r square. Let A be the region bounded below by the cone and above by the paraboloid c is equal to minus 2 minus 1. Set up a triple integral into cylindrical coordinates to find the volume of the region using the following orders of integration. So dc dr d theta and then dr dc d theta. So they said this paraboloid, no wait, this cone, right, and then this paraboloid bounded by below by the cone and the, okay, so they mean this section, this section inside here, not including this or this. And what do they do? First they evaluate c, right, from z is equal to r, so to z is equal to 2 minus r square. I don't understand. Z is equal to r. Yeah, in the polar coordinates, r would be here. Then why is it z is equal to r? The cone is of radius 1 and where it meets the paraboloid, since c is equal to 2 minus x square minus y square, or which is equal to 2 minus r square, and c is equal to r. Assuming r is not negative, we have 2 minus r square is equal to r. Solving, we have this. Since r is more than 0, we have r is equal to 1. Therefore, z is equal to 1. So the intersection of these two surfaces is a circle of radius 1 and the plane z is equal to 1. The cone is the lower bound for z and the paraboloid is the upper bound. Projection of a region onto the xy plane is a circle of radius 1 centered at the origin. You can describe the region as Okay, I think they got r from here and then 2 minus r squared from here. So I think when we do this, z is going from here, the bottom of the cone, to the top of the parabola. We're summing these, all of these z. R is from 0 to 1. Uh, R can be negative 2 or positive 1, and we have R is equal to 1. Okay, so from 0 to 1 and theta from 0 to 2 pi. Yeah, this was a little confusing, but I get what they did. Let E be the region bounded below the R theta plane, above by the sphere x square plus y square plus z square is equal to 4. And on the sides by the cylinder x square plus y square is equal to 1. So we are considering this outer shell, right? Set up a triple integral in the cylindrical coordinates to find the volume of the region using the following orders of integration, and in each case, find the volume and check that the answers are the same. dz dr d theta dr dz d theta. So dz, you make z the subject over here. We need these, right? X squared plus y squared is r squared. So z squared is 4 minus r squared. So z should go from 0 to 4 minus r squared. R should go from 1 to from 1 to this endpoint. This endpoint is from 1 to the sphere, right? And theta goes from 0 to 2 pi. So 0 to root 4 over minus r square, that I understand. 0 to 2 pi, understand. 0 to 1, that I don't understand. Why is it 0 to 1? Equation of the cylinder x square plus y square or r square is 1. Yeah, but that's the minimum, right? On the sides of the cylinder. Set up the integral in a cylindrical coordinates. Okay, I think we are finding the volume inside the cylinder. But the top is covered by the sphere. The top is not straight. That's what I understand. But above by the sphere and on the sides by the cylinder. Okay. Side is by the cylinder, the above is by the sphere. Okay, then I understand. Here spherical coordinates, we have phi, no, rho. This is rho, right? Rho, which is the length of this, the distance between the origin to the point. Then we have theta in the xy plane, and then phi. So theta is from the x-axis, and then this phi is from the z-axis. So x is phi sine theta, sine phi. So rho sine phi, sine. So okay, so rho sine phi gives the r value, and then r cos theta gives the x value. Phi is rho sine phi gives the r value, and then sine theta gives the y value. And rho psi phi, rho cos phi gives the z value. So integration we have the triple integral in the spherical coordinates is the limit of the triple Riemann sum. F is rho star theta star phi star, then rho star square sine phi squared. Yeah, this one is complicated. Set up an integral for the volume of the region bounded by these cone. C is equal to root 3x square plus y square. The hemisphere Z is equal to root 4 minus x square minus y square. So we are finding the volume of this inside region, right? So Z goes from root 3 R. Yeah, root 3 R to root 4 minus R. But then R we have to convert it to the other coordinates. What do you call this? Spherical coordinates. We have this, and then we have rho square is equal to 4 or rho is equal to 2. So from 0 to, okay, wait. This rho cos phi. Wait, why from 0 to 2? 0 to 2, 0 to, okay, 0 to pi over 6. And then 0 to 2 theta. Theta is 0 from theta to 0. From theta 0 to theta is equal to 2 pi. Right. I wanted to read more, but I wanted to do more exercises, but I will end the stream here for now. I'm getting quite sick. Then I'll do some of this in my alone time, and then I will read the next chapter later. Anyways, see you guys next time. Bye.